Flexural-Torsional buckling. In many cases, structural engineers may see themselves in a situation where they have to deal with singly symmetrical steel members. In this tutorial, I will show you how easy it is to design such members when they are subjected to axial compression. Please note that the examples found in this tutorial will be solved in accordance with the 14th edition of Steel Construction Manual by Aisc. Flexural-torsional buckling is an instability failure mode that occurs in members subjected to compression. The result of this failure mode is a combination of flexural buckling of the member and torsional buckling of the cross-section. This type of failure can occur only with unsymmetrical cross-sections with one axis of symmetry, singly symmetrical shapes, such as structural tees and channels. For singly symmetrical shapes, align the cross-section of the member so that y-axis is the axis of symmetry and x-axis is the axis of no symmetry. X-axis is subjected to flexural buckling only, and y-axis is subjected to two buckling actions, flexural buckling and torsional buckling. These two actions occur simultaneously. That's why we call this failure mode flexural-torsional buckling. Since there are two actions in flexural-torsional buckling, then the source of strength will be a combination of flexural and torsional actions. Now, let's illustrate graphically the two failure modes associated with these structural members. When bending is about the axis of no symmetry, we have flexural buckling only. When bending is about the axis of symmetry, we have a flexural buckling and twisting of the cross-section. These two actions occur simultaneously. Here, we are looking at the column from an angle perpendicular to the first one. Example 1. Here we have C15 by 50 of A36 steel. The effective length with respect to X, Y, and Z axes are each 13 feet. It's required to compute the compressive strength of the member. Use LRFD method. Section E4BII of Aisc specifications applies to this example. This figure shows the original position of the cross-section. Now we need to align our section so that y-axis is the axis of symmetry and x-axis is the axis of no symmetry. 1. Compute the flexural buckling strength about x-axis, the axis of no symmetry. Calculate the slenderness ratio KL/R. Since we have switched the axes of the cross-section, Rx in this example will be Ry in the Aisc specifications, and Ry will be Rx, where R is the radius of gyration of the section. KL is the effective length and it's given. Notice that the effective length, 13 feet, has been multiplied by 12 to convert feet to inches. Now we have a slenderness ratio of 180.3. Compute the elastic stress, Fe. If we substitute for the unknowns in this equation, we will get Fe of 8.805 KSI, where E is the modulus of elasticity of steel. Modulus of elasticity of steel is 29,000 KSI. Determine whether the flexural buckling falls within the elastic range or inelastic range. Now we have to calculate the limiting value 4.71 multiplied by the square root of E over Fy, where Fy is the yield stress of steel. In this question, Fy is given, and it's 36 KSI, since A36 steel is being used. Now, if you substitute for the unknowns, you'll get 133.7 for the limiting value. Since the slenderness ratio KL over R with respect to X is greater than the limiting value 4.71 multiplied by the square root of E over Fy, then we have elastic buckling, and Aisc equation E3-3 applies. Calculate the critical stress, F critical, or FCR. The critical stress equals 0.877 times Fe. Now if you substitute for Fe, you'll get a critical stress of 7.722 KSI. Note that 0.877 is a reduction factor to account for the effects of initial crookedness in the member. Now we are ready to calculate the nominal strength Pn. Pn equals the critical stress times Ag. Ag is the gross cross-sectional area of the member. Now if we substitute for the unknowns, we will get a nominal strength Pn of 113.5 kips. 2. Compute the flexural-torsional buckling strength about the y-axis, axis of symmetry. Calculate the slenderness ratio with respect to y-axis, KYL over RY. Notice that the effective length 13 has been multiplied by 12 to convert feet to inches. Now we have a slenderness ratio of 29.77. Remember, the limiting value 4.71 multiplied by the square root of E over Fy is 133.7. Since the slenderness ratio is less than the limiting value 4.71 multiplied by the square root of E over Fy, then we have inelastic buckling, and Aisc equation E3-2 applies to our solution. Now we are ready to calculate the critical stress. The critical stress equals 0.658 to power Fy over Fe, the whole thing multiplied by Fy. The question is how to calculate the elastic stress Fe. It is a three-step process. Step 1. Calculate Fey using equation E4-8 found in the Aisc specifications. Now if you substitute for the unknowns, you'll get Fey equal to 323 KSI. Fey is the resistance to flexural buckling. Step 2. Calculate Fez using equation E4-9 found in the Aisc specifications, where G is the shear modulus of elasticity in KSI. J is the torsional constant or polar moment of inertia in inch to power 4. CW is the warping constant in inch to power 6. And R0 bar is the polar radius of gyration about the shear center in inches. The first term between brackets multiplied by 1 over Ag times R0 bar squared represents the warping torsional resistance. The second term multiplied by 1 over Ag times R0 bar squared represent the Saint Venant torsional resistance. Now if you substitute for the unknowns, you'll get FEZ equal to 80.06 KSI. FEZ is the resistance to torsional buckling. This figure shows the warping deformation of the cross-section of a wide flange member under torsion. Here, the flanges warp against each other and both will be out of a plane of the member. When out of a plane warping deformation occurs, shear stresses in the flanges will be developed, resulting a couple that resist the torsional moment. Step 3. Calculate the elastic stress, or Fe. To calculate Fe, use equation E4-5 found in the Aisc specifications. Now, if you substitute for the unknowns, you'll get Fe of 78.46 KSI. The term H found in equation E4-5 can be taken directly from the steel construction manual. Notice that the resistance is a combination of flexural buckling resistance and torsional buckling resistance. Now we are ready to calculate the critical stress. Now we can substitute for the unknowns to get the critical stress. If you do so, you'll get critical stress equal to 29.71 KSI. Now let's calculate the nominal strength Pn. Pn equals critical stress multiplied by Ag. Pn equals F critical times Ag. Substitute for the unknowns, you'll get Pn of 436.7 kips. The smaller value controls the solution. Therefore, the flexural buckling strength controls and the nominal strength is 113.5 kips. Finally, we need to calculate the design strength. To get the design strength, multiply the resistance factor by the nominal strength. The resistance factor in this case is 0.9. Now, if you multiply 0.9 by 113.5, you'll get a design strength of 102 kilopounds. Example 2. In this example, we have WT 12 by 81 of A992 steel. The effective length with respect to the x-axis is 25 feet 6 inches. The effective lengths with respect to y and z-axes are each 20 feet. It's required to compute the compressive strength of the member. Use LRFD method. Section E4.A of the Aisc specifications applies to this example. Now, if you check the cross-section of the member, you'll see y-axis is the axis of symmetry and x-axis is the axis of no symmetry. Therefore, we don't have to change the position of the cross-section. 2 points are shown in our cross-section. The first point is the center of gravity of the cross-section. The second point is the shear center. Shear center is a point through which if the external load passes, then there will be no twisting of the section. The reader can go back to any textbook in mechanics of materials to learn more about shear center. 1. Compute the flexural buckling strength about the x-axis or axis of no symmetry. Calculate the slenderness ratio with respect to x-axis, KL/R. If you substitute for the unknowns, you'll get a slenderness ratio of 87.43. Notice that the effective length with respect to x has been multiplied by 12 to convert feet to inches. Calculate the elastic stress, Fe. If you substitute for the unknowns, you'll get an elastic stress of 37.44 KSI. Determine whether the flexural buckling falls within the elastic range or inelastic range. Therefore, we have to calculate the limiting value 4.71 multiplied by the square root of E/Fy. E is the modulus of elasticity of steel, and Fy is the yield stress of steel. Since we are dealing with A992 steel, then Fy should be taken 50 KSI. Modulus of elasticity of steel does not change and is equal to 29,000 KSI. Since KL/R, or the slenderness ratio, is less than the limiting value 4.71 multiplied by the square root of E/Fy, then we have inelastic buckling, and Aisc equation E3-2 applies to solution. Calculate the critical stress, F critical or FCR, using the following equation: 0.658 to power Fy/Fe, the whole thing should be multiplied by Fy. Now if you substitute for the unknowns, you'll get a critical stress of 28.59 KSI. Now we are ready to calculate the nominal strength, Pn. Pn equals F critical times Ag. Now if you substitute for the unknowns, you'll get Pn of 683.3. Again, Ag is the gross cross-sectional area of the member. 2. Compute the flexural-torsional buckling strength about the y-axis, or the axis of symmetry. Now we need to compute the critical stress. How to calculate the critical stress F critical? It's a 3-step process. Step 1. Compute F critical Y. F critical Y is the resistance to flexural buckling. Calculate the slenderness ratio with respect to Y, KL/Ry. Now if you substitute for the unknowns, you'll get a slenderness ratio of 78.69. Remember, the limiting value 4.71 multiplied by the square root of E/Fy equals 113. Since the slenderness ratio with respect to y-axis, KL/R, is smaller than the limiting value 4.71 times the square root of E/Fy, then we have inelastic buckling, and Aisc equation E3-2 applies to our solution. Calculate the elastic stress Fe. Fe equals pi squared times E divided by the slenderness ratio with respect to y squared. Now if you substitute for the unknowns, you'll get Fe equal to 46.22 KSI. Now we are ready to calculate F critical y. F critical y equals 0.658 to power Fy over Fe, the whole thing multiplied by Fy. Now substitute for the unknowns. If you do so, you'll get F critical y equal to 31.79 KSI. Step 2. Calculate F critical Z. F critical Z is the resistance to torsional buckling. Since the shear center of a T-section is located at the intersection of the center lines of the flange and the stem, then x0 equals 0, y0 equals y bar minus T flange over 2. Now if you substitute for the unknowns, you'll get y0 equal to 2.09 inches, where x0 and y0 are the coordinates of the shear center. Calculate R0 bar squared using equation E4-11 found in the Aisc specifications. Now if you substitute for the unknowns, you'll get R0 bar squared equal to 25.87 square inch. Now we are ready to calculate F critical Z. F critical Z can be calculated using equation E4-3 found in the Aisc specifications. Now if you substitute for the unknowns, you'll get F critical Z equal to 167 KSI. Remember, G is the shear modulus of elasticity of steel, and this value is 11,200 KSI. Step 3. Calculate F critical. Now we need to calculate the sum of F critical Y and F critical Z. The sum of F critical Y and F critical Z is equal to 198.8 KSI. Now we need to calculate the term H. The term H can be calculated using equation E4-10 found in the Aisc specifications. Now if you substitute for the unknowns, you'll get H of 0.8312. Remember that the steel construction manual does not provide the values of term H for T-sections. Instead, the term H should be calculated using equation E4-10. Finally, we can calculate F critical. F critical can be calculated using equation E4-2 found in the Aisc specification. After substituting for the unknowns, you'll get F critical of 30.63 KSI. Notice that the resistance is a combination of flexural buckling resistance and torsional buckling resistance. Now we are ready to calculate the nominal strength Pn. Pn equals F critical times Ag. If you substitute the values, F critical equals 30.63 and Ag equals 23.9, you'll get a nominal strength Pn of 732.1 kips. Now, which value should we pick for our solution? The smaller value controls the solution. Therefore, flexural buckling strength controls and the nominal strength is 683.3 kips. Now we need to calculate the design strength. The design strength can be calculated by multiplying the reduction factor phi or phi by the nominal strength. For buckling, the reduction factor phi or phi equals 0.9. Now if you multiply 0.9 by 683.3, you'll get a design strength of 615 kips. Let's summarize the differences between channel and T sections when it comes to flexural-torsional buckling. For channels, the critical step is Fe. To calculate Fe, you have to go through 3 steps. Step 1, calculate Fey. Step 2, calculate Fez. And step 3, calculate Fe. For T sections, the critical step is F critical. To calculate F critical, you have to go through 3 steps. Step 1, calculate F critical Y. Step 2, calculate F critical Z. And step 3, calculate F critical. In this slide, I'm showing you the location of the shear center and center of gravity for different sections. Before we finish this tutorial, I would like to draw your attention to equation E4-5 of the Aisc specifications. Notice that the first term is implicitly incorporated into the term under square root. If we denote the first term of the equation by big omega, then we can rewrite equation E4-5 as in a similar manner, equation E4-2 of the Aisc specifications can be rewritten as